today I remember. Yeah. So hybridization is the combination of two or more orbital to form a new orbital that have the more unique character and more stability. So valency bond theory and molecular orbital theory, these two together overlap and eventually the covalent bonding happen and compound form. Now here let's see a little bit of review about the molecular orbital. Electron shared between all nuclei, multi-center bonding. Hybridization, electrons share between the two nuclei, two center. So the thing is that last time when we saw, here we saw the total things, and here we are going to see the how the specific two nuclei and two center like carbon and hydrogen. So the electron of hydrogen and electron of carbon, they will be shared their electron so towards the carbon nuclei and carbon one towards the hydrogen nuclei. This is how actually the bond formation happens. Now, what atomic orbitals are involved in the overlap? As I say, combine or overlap. Let's see the correlation between the electron or geometry around atom and the shape of. So when we have the linear or different shape, we have also their correspondence hybridization. We can now sort it down here. So let's see. Electron pair around atom. 2, 3, 4, 5, 6. Electron geometry 2, linear 180. This is sp. When sp, that means one s orbital and one p orbital overlap and make the two sp orbitals, hybrid orbitals. This is at the shape and hybrid orbital. This is the hybridization of the atom or orbital, atomic orbital. And here the geometry shape that yesterday we check it out. The ballistic three-dimensional structure and what about their distance. Here the trigonal 120 degree, when it will be trigonal, you remember the most important thing is here. So sp, here if we have 3 sp2, so total will be 3. So 3 sp2 orbital. Here is a 4, 3 sp3. So 4 sp3 orbitals. How it will become, we will be learning very soon. Trigonal bipyramidal 120 and 90. Here trigonal, their atomic number is also higher and their electron pairs, you can see, also higher. So it will move on to the even d orbital. So dsp3 and this amount will come. And octahedral d square, I mean the d2 sp3, this amount of orbital can be formed. You will have the multiple choice question that if one s orbital and one p orbital overlap, how many hybridization orbital will be formed, or what type of orbital will be formed. So when we will be explaining, it will be more clear like that, but you have to be answer like that when. So how? Let's move on. Linear geometry or sp hybridization. Yeah. So in another sense, we can also say the hybridization actually the mixture of orbital that results from combining or merging more atomic orbitals, and the concept of hybridization, the concept of do the hybridize or mixed is called the hybridization. And here electron either mostly excited or electron promotion from different energy state level happens. Now let's see here. Carbon has the 4 valency orbitals. That means, we have a 4 valency electron. So that means carbon have a 4 valency orbital. How? We are going to see, like, we remember 1s, this is hydrogen. But when we are going to 1s2, 2s2, 2p6, then 3s to 3p6. So we consider each one is one orbital, correct? So this way we need to count. So carbon has 4 valency orbital available for bonding. We know sometimes we talk about the 4 hand, that are the valency orbital for available for bonding. See, carbon is a linear geometry or 180-degree angle. How do we get 2 atomic orbitals to form the bonding orbital with a bond angle to 180? So here we have the S and P. P we have also 3. Here we have one tone. So when our question will be telling you only P, you have to consider the Px, Py, and Pz. So this we have to also consider. So let's move on how. Here we show how do we get 2 atomic orbitals to form the bonding orbital with a bond angle of 180. So here we have the unhybridized Py and Pz orbital. And here we have sp hybrid. So actually what happened, let's consider this is S. Let's take the another color. Let's consider this is P. So what happened, they actually come together like that. And we will become talking that the sigma, so some head to head, this is called the head one, we have head to head, and one we have line. So head to head means the sigma bonds. So we will be coming. So 1 2s and 1 2px equal to 2 sp hybrid orbitals. So initially for carbon we have one 2s and one 2px, and we will make 2sp hybrid orbital. The hybridization of s and px atomic orbital results in the formation of 2sp hybrid orbital, like that. As I said, s and p, they will be make one this, because we have the 2s, one s, one p, another s, another p. So this is how they will combine and make the hybrid orbitals. Now, yeah, I actually have the another lecture that I show the details about the SP, SP2, SP3. That was more straightforward, but anyway, at this moment I don't have it, so move on. Trigonal planar geometry, or SP2. So here we have one s and two p orbital. So when one s and two p orbital will be combined, they will be hybridized and make a sp2 orbital. Boron has 4 valency orbitals available for bonding. So here boron has 4, but here we could see the 3. Okay, let's see. How do we get 3 atomic orbitals to form bonding orbitals with the bond angle 120? Yeah, let's move on, then we can. We are now talking about the 4 valency, so let's see. Could you anybody check the atomic number of boron? Is it 7? I mean, is it 6? I think carbon 6, correct? Boron, could you check it out? What is the atomic number of boron? 5? Yeah, so I think here is just typo, okay? Here is just typo mistake, okay? Because last slide had a carbon 4. So when we make a slide, because it make not at this stage C 3 atomic orbital. So 5 means that first stage 2 and the final, I mean, valency 3, okay? So here will be the 3, okay? Just to make sure. Yeah. So next, now see. In this case, what will be happen? 2s, 2px and 2py. So it will be total 6. How? Like 1s, 1p, another s, another p. So spx, spy, again spx, spy. So this is how we can find the 3sp2. So s and p orbital, 2p orbital will be combining and make a 3sp2 hybrid orbitals. So they will just combine and make. Here we could see how it works. Px, px, py, and this is the x. So here they have, you see, this is how they are combining. And finally, they are making it. Tetrahedral geometry sp3. This is, yeah, here I have this one. sp3 sp3 like methane, CH4. Yeah, that because I wanted to tell you something, that how actually bond formation happens. Let's draw here. I will little bit of show, otherwise it may not be like that. This is look into how I'm making carbon forehand. So then you will also got that sp2, sp1. So this is the carbon forehand. We know hydrogen have only S, correct? So what happened? Change the color. Let's see, the green one is hydrogen. So hydrogen will come here. This is called the head-to-head. That's the sigma bond they form. Sigma bond is more stable and more strong. So these are the hydrogen, these are the carbon hand or valence electron. So when they make this type of overlap, this is called the, this is very famous and useful when we talk about the hybridization, sp3r, here we go, the carbon. So actually, this is a way the carbon hydrogen bond is formed by sp3, S overlap. So now I want to tell you something. Carbon have one s orbital and three p orbital, and hydrogen have only one s orbital. So this only one s orbital, and carbon have s and p orbital. When they overlap, they produce the sp3 orbital. And this how many? Because we have here 4 valency, so 4, total 4. So S to here, S to here, S to here, and this is how we will find. So when you will see the central valency, you will guess the how many. Now when you will have the more bigger atom, like this is called methane. So now if you have ethane like C2H6, that time the scenery will be changing, because that time we will have the carbon carbon double bond. So when double bond come, one get the sigma s2s head to head, and another the sharing of electron, the cloud, that are not so much. So that I think we are going, I saw they have some, so we can discuss, but this is how actually happens. And when we are talking about the, this is the trigon, oh, no, not this one, this one. Yeah, so this is the angle when we are talking about, this is 109.5. How you consider we draw like that? I want to show you how we draw. I will post this one, so don't worry. Here we draw like that. These two, this is not the perfect one. I just showing that, sorry, like that, like that. So this is a kind of angle that make, when the shape is like that, they make this amount of angle. Here, carbon and hydrogen head-to-head bond form. So actually, this is the mechanism for the hybridization, how the hybrid orbital form. And we can also write something else to make you clear more. So actually, what is going on here? We say that this is 4 counts. So how the 4 counts? So let's spin here, right? 1 S and 3P. 1, 2, 3. Correct? This is sp3. So we have 3p, p, p, and p. So from here, because p again px, py, pz. So from here, we will have the 4 sp3, 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 and sp3. So this S will do with every and make this type of. So this is called the 4. So what I have here, because why 4? Because here carbon have a 4 valency and we have the 4 hydrogen. So they make this type of bond. So this is called the sp3 or the hybrid orbitals. And this is head-to-head overlap that comes from carbon and hydrogen. Theta, yeah, that I was wanted to show the things. So actually tetrahedral shape is like that. This is not actually, sorry, like that. This will become like that. So these angles are 109. The mixing of, as I said, that do not take it so complicated. This is not complicated. This is simple. Just when the two things mix and form the another new things. Like when you mix the two color, you will find that different color, correct? So do anybody know when you guys are at school? I think you play the color mixing or something. Do you know that how we can make the white color from other colors? So you know we have the when we add the red blue comes different color, correct? So similarly when we mix all color, actually comes a white color. So this is kind of thing. When you will give the how many that you are giving, they will mix and they will be giving the hybrid and they will make the new orbital. So see the question is like that. The mixing of one s atomic orbital and the two p atomic orbitals produce. So we know then 1s and 2p. Actually, this is sp2. So what will be the answer? This will be. So how many you have? Actually, after overlapping, the number of will be like that. Okay. So if you have sp3, 1s3p, so total will be 4. If you have s and p, total will be 2. Got it? This is how. This is not so complicated. So don't think as a complicated. The mixing of, yeah. So how it comes? Let's look into here. 3sp2. So 1s, 1px. 1x, 1px, 1py. 1x, 1px, 1py, 1pz. So this is how many will become. Okay, this is if you look. That's just a mixture or overlapping, nothing the rocket science or something. See, they have whatever the angle I try to draw, they have here. So trigonal bipyramidal, sp3 also D, because it depends on, this is phosphorus. You know the phosphorus atomic number is I think high. So if you read the phosphorus electronic configuration, so how many phosphorus? Yeah, see, this is phosphorus 3sp. They don't have the D. Let's see, look back. Phosphorus pentachloride. Okay, I will be check out this one. But anyway, since this is the 5, oh, I see. Now I got it. Phosphorus has the trigonal bipyramidal geometry when they have the 5. Okay, this one is the D. Okay, let's see. I think I need little bit of additional explanation. I will give you because I need to check it out. So third row elements have the D orbital. Third row elements, periodic table, third row. Periodic table is amazing thing. Phosphorus. Oh, 1, 2, 3. I see. 1s2, 2s2, 2p6, 3s2, 3p, 4sd, 4p. Sorry, I need to little bit of check it out because D start from here, correct? I will check it out, okay? Yeah. Anyway, let's go back here. So third row elements have d orbital. I have to check it out. So you don't need to go too much here. Just let's see it. And if I find any explanation, I will. So here, phosphorus pentachloride. So we have this type of structure. And since this is how many? This is sp3d. See, look into sp3d. So how many orbital involved here? Here is a 1, 3, and d, 5. So the result total hybrid orbital will be 5. Okay? This is the simple calculation when you will answer your multiple choice questions. Octahedral 8. So how many we have? sp3d2. 1, 2, 3, 4, 5, 6. So 3, 2, 5, 6. Here will be 6. Though this is octahedral shape. Yeah, see here? It will be 6. And this is the shape. Here the D2 and sp3. So these are the some example. The AsF6 anion has octahedral electron geometry. The hybrid orbital used by the S atom for bonding to the F atoms are, how many we saw? We saw D2sp3, correct? Let's see, go back. Yeah, D2sp3. This is how you have to practice and study. So we have here the sp, sp2, sp3, and also some other additional we saw. This one is octahedral, D2sp3. Before that we saw trigonal and pyramidal sp3d. You just need to be little bit of remind here. Now, as I say, the head-to-head and like that type of things. So actually what happened, the orbitals are wave function, whatever. So actually we are talking about here sp, sp2 or sp3. Waves can interact constructively or destructively. You know, last time we saw in the phase, out of phase, when they are in a right medium, they will make it combine and the amplitude, the height will be double. But when they are not in a same phase, out of phase, they subtract and they will make the destructive or linear. That last time we saw. So that linear is the pi bond actually. And when the head-to-head, this is called actually the constructive or sigma bond. They are more stable. And I also want to give you one trick. The single bonded compounds are only sigma bond, okay? When double bond, triple bond will come, that time pi bond introduction, that means the this type of linear bond also will come. They will also share some electron, because eventually they all want to be either octet or duet. So that's the reason when double triple bond will come, you will see the existence of pi bond, but when the single bond, that will be the sigma bond. See the constructive overlapping or sigma bond. Okay, so here we will have, this is the head-to-head bond. When orbitals interact head-on, this is actually, it depends on language, book to book or something. We say the head-to-head and the linear one. So sigma bond sharing, two electrons, single bond. Okay. This is how sigma bond work. When orbitals interact head-to-head, they form a sigma bond sharing. This looks, and the pi bond. I have the very nice configuration. Yeah, so I will upload as a supplemental and I will show you later. So what happened actually? if you have the double bond, how the sigma and pi bond happen. So one, let's consider here. The pi bond introduction I want to show. So we know the carbon have a 4 bond. So if when two carbon are overlapped, that means they're already sharing here 2 bond, and here will remaining. So here the 2 bond, 1 sigma and 1 pi. So the sigma bond like they are head to head, and here with some electron cloud. So this area and this area, these weak electrons from both the carbon, they share and make the pi bond when you have double or triple bond. Okay, but in that case, look into the sigma bond first, that what are the visual representation is here. That see, if you have here like that, then sigma bond will form head to head. But if you don't have, if you have like head and tail like that, they will not form. If you have this way, they will not form. So they have to be right way to come to make the sigma bond. Head-on overlap will result in the formation of sigma bond, sp, sp2, sp3, and 1s. So they will be making it the head-to-head sigma bond. I think that I already discussed how it makes, and you guys have here. Never scare your presentation, because I have sometimes seen they have lots of number of slides, but actually the topic not so much. Okay? Yeah. So don't be scared. This is a kind of nowadays the marketing policy. So if you just sometimes go through the subway station and you will see lots of new company, sometimes they will stop you and they will start, especially the electric and phone mobile, the kind of thing that they will show you that we are lots of things, we are many things, but actually no, thing is small. So what we already talked, we have here. So look into. Yeah. So when you make sp2 hybrid, the pz orbital remain unhybridized. The reason is that as I said, sp2, we have px, py, and pz. So obviously when sp2, this will be unhybridized. See this, that I was trying to show you. So these axes, they are going to consider lateral for the. So see here. So they will be making a bond, and other will be planar. So pz orbital remain unhybridized and is perpendicular to the plane of the hybrid orbitals. So like this type of shape they will have. This is called the side-to-side overlap, also called. See here the pi bond that I was trying to say. Both loops of electron density contribute to one pi bond. So whatever we have, they will side by side, they will contribute to one pi bond. And these are the head-to-head sigma bond. So when p orbitals interact constructively, they overlap side by side that I was talking and form a pi bond sharing 2 electrons. These are distributed in both loops of electron density. So this is how they will make it. Orientation matters for the bond formation. For maximum pi bonding, p orbitals must be parallel to each other. As I said, that will be like that. So they need to be parallel. If they are not parallel, pi bond will not be formed or overlap. Formation of sigma bond. Each C in ethene, this is called the ethene. So C2H6 called ethane. But when the ethene comes, 2 hydrogen less, because here the 4 bond, so like that. So that time we have sp2. sp2 means total 3 hybrid orbitals will come. But here one will be head to head and another will be pi. Let's see, I think they have it. Here we go. So these are the sp head to head. These are head to head. Carbon H, carbon H, carbon H, head to head. Even this one is also carbon carbon head to head. So the sigma bond formed from head on overlap of the sp2 hybrid orbital. Now let's see what is going on. Here we go. You know, we have the unhybridized p orbital that are going to make the parallel and pi bond. Now got it? So we have here sp2. That means we saw that one s and px, py. So that will be overlap hybrid and new orbital sp2. But still we have some unhybridized pz. So that will be make the like that parallel and they will become together. They are normally weak. As I said in the beginning, that why we need hybridization or overlap, because when they combine together, their stability and their character will go rise. So obviously unhybridized are not so strong like the hybridized. So they are very weak, and if they are perpendicular or like that parallel, they can come close due to the electron cloud or density, and they can make the pi bond here like that, this way, this way. So unhybridized p orbitals lie above and below the plane overlap to form the pi orbital. Got it? Yeah. So now I have one simple question before move on. This is the sp2. Now if I show you one, can anybody say that how many pi orbital can be here? This is called the acetylene. So anyway, when we have this type of situation, here will be sigma, here will be sigma. But sp means two orbital hybrid orbital will come sp, so px, so py and pz will be unhybridized. So can you tell how many then pi orbital will come? Last one was sp2, so pz was unhybridized, and that's why one pi bond came. But if you have a 2p unhybridized, then yes. Yeah, so you guys can look into here. See, this is sigma, this is pi. They show how they will making. So what hybrid orbital are used to form the sigma and pi bond in diatomic oxygen? I think diatomic oxygen is like that. So if you move on, yeah, see, sp2p. So sp2p. Why sp2p? An atom with a double bond and two lone pair will always be sp2 hybridized. What hybrid or atomic orbitals are used to form sigma and pi bond? Oh, okay, got it. So for the pi bond, they are talking here the p orbital, unhybridized. So that's why they write like that. Yeah, this is sp2 because we have the double bond. So that means one p is unhybridized and that will make the pi bond. So actually here, one bond will be, this one will be sigma, and if I use the different color, so here will be unhybridized pz, they will make the another pi bond. So that's why like this one is pi bond and this one is sigma bond. Now the got it? This is how it will work. Yeah, same thing as I said. So it's easy, it's not tough, huh? You need to just understand. Same thing that I just draw here, see? Unhybridized. So remember, the hybridized orbital will form the sigma because they are mostly head to head. They make more stable sigma band, and when we have some unhybridized, they are also can make, if they are in a perpendicular or parallel, normally they are weak because they are not hybridized to make something strong. So nowadays, you know, nowadays different products in the market. First come the like iPhone, then come the iPhone Plus, then like for example iPhone Premium, then it will come iPhone exclusive. So this is how it comes here also like that. When you will combine something, obviously, when we are a child, we always teach that if you can work in a team, you will be most strong, and you cannot do alone everything. Correct? If you have a heavy thing you want to try, it's not possible. But if 4 or 5 people come together and unite, then it's going easy. So when you will combine something together, the result comes always more stable and strong. Yeah, I already talked the triple bond one, you can see here. So how the 1 sigma and 2 pi bond comes. The lone pair on each nitrogen is held in a sp hybrid orbitals. How many sigma and pi bonds are there in the following organic compound? So here 1 pi, here 2 pi, 3 pi. But now sigma, 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 sigma. 1, 2, 3, 4, 5. Let's check it out. But why they are taking 9 sigma? Oh, okay. They also have here. Sorry. Yeah, you are right. Here we have also 1, 2, 3, 4, 5, 6, 7, 8, 9. Got it? Okay, let's circle down. 1, 2, 3. Because when you will see the double bond, obviously 1 pi bond. So 1 sigma, here is 1. 1, 2, 3, 4. Here we have 1. Single bond, 1 sigma. 5. Here we have 1. 6. Here we have 1. 7. Here we have 1. 8. Here we have 1. 9. Got it? Free rotation around a single bond. Yeah. You know, last class I talked about the ball and stick. When you have it's very simple that if you have something, stick and ball in your hand, you can rotate down. But if you have double bond, that makes you more rigid due to the pi density. So that's very difficult. Here it's a little bit of rigid for the double bond, and it's not so easy to rotate. But if this is free or single bond, it's very easy to 36-degree rotation normally. So single can rotate freely 360-degree, and they are mainly sigma. And the double or triple bond, they cannot move freely in 360-degree because of pi density. Above and down or below the plane makes the bond very rigid, as I just said. For some practice, we have here. I also don't know what this is. Let's see. Can we go here? Higher education support. Okay, you guys can practice. If you see something, I think I go from there. Yeah. Yeah, you have in your slide, so you can see there. Isomer. You know, isomer are kind of things, their molecular structure, molecular weight, and their composition is same, but location is different. Then this is called isomer. So one compound can have 2, 3, or more different orientation, like carbon, hydrogen, or different groups orientation, and we can say a different name. Like here, if we look into here, same compounds, we have here H, H, Br, Br. But we can see the thing here, look into here, the orientation of bromine change, correct? So that's how this is isomer, and we will be little bit of talking here. Actually, this is part of organic chemistry. You have to do lots of things here when you will go to the organic chemistry. Identical Lewis structure. 1,1-dibromomethane. Sorry, ethane. Yeah, C2. So ethane. Methane CH4. And ethane C2H6. So 1,1, this position, 1,1-dibromoethane. So that means 2 hydrogen atom of the ethane replaced by the bromine. Okay, so let's see there. Lewis structure, how we can draw. So if you look into here, how many structure we have? First look into here. 1. See the bromine, here is the change. See, here is the change. Here is the change. Yeah. So this is how, same molecular formula, but the different orientation, and their name is also some different for that reason. There are 3 more Lewis structure. Can we find them? So we find here 3. Is there any more? Oh yeah. So see here, if we just rotate, free rotation, we saw if we rotate 360 degree, it can also go this way, correct? Yeah. So let's see what we have more. See? So we have to actually count the valence shell, and then we have to find that it is more or not. So that's all actually you have in this chapter. This is just, you have the little bit of definition that what are the isomer, but actually you will go to the next, I'm not sure, general chemistry. Yeah, this is the isomer actually. Different types of isomer. See here. So structural isomer, stereoisomer. So that is going to be your 2-3 chapter. I think first quarter of your semester, your teacher will be teaching practice and those type of things. But as a part of basic, you have little bit of just hints what is isomer. So that was all. Please practice. As I say, you don't need to go so many places. Follow on the lecture, and you don't have these chapters as part of your first examinations. So yeah, this is the lecture, second lecture examination. Yeah, so please practice it. Some questions you have. Yeah.